Hey guys, so I decided to record a video for this Desmos demonstration in regards to exponential, linear, or quadratic regressions. Okay, so this Inspire one that I created before is good to go and definitely use that for sure. But if you don't have access to, let's say, an Inspire at home and you wanted to use Desmos, please understand that we did share with you on your Google Classrooms a free online calculator as far as downloads for the CIS, for the TI-84, and also this other online calculator that you could use. We want you to first go to those, but if you're having trouble downloading those for some reason, then go to Desmos and rely on Desmos afterwards. But please don't have Desmos be your first go-to if you can help it, okay? All right, so let's go ahead and talk about this. I'm going to use the same numbers that I used in this example video for the Inspire so that you can see how the answers match up. But before we go to Desmos, which I already have open right here, we have to see a couple important parts of how we're going to put it into Desmos, okay? So we're going to look at this chart right here. And the three functions that I'm going to be putting into this video that I'm going to demonstrate to you are the linear, quadratic, and exponential, okay? So the parent function is y equals x for linear, and a familiar form from Algebra 1 that you remember is y equals mx plus b. So when you do regressions in Desmos form, you're going to have this is y equals mx plus b. And this is y equals mx plus b for a regression, okay? So with the regression, because you have an x and a y column in the table, you have to put x and y like this because x and y are also changing. It's looking at like column 1 for x's and column 1 for y's. And then this tilde symbol is signifying like that equals, but with the regression. That's how Desmos software knows that you're trying to create a regression, okay? Quadratic, you're used to the parent function y equals x squared. The familiar standard form is y equals ax squared plus bx plus c. So we're going to mimic, again, this familiar form and transfer it to Desmos form by y equals ax squared plus bx plus c. Again, the x and the y are going to need this kind of subscript of 1 because you're going to be getting it from the table that you're going to create right here. Okay, so this is x1 and this is y1. That's where these values are going to come from, okay? And then finally, exponential. You could have 2 to the x, 3 to the x, where it doubles or triples each jump. Or you could have e to the x, all kinds of numbers as far as the base is concerned, and those are in other videos in this unit. But the familiar form is y is equal to a times b to the power of x. So when we transfer that familiar form into Desmos, it's going to be, again, y subscript 1 is tilde with a, and this is that regression kind of symbol, times b to the power of x sub 1. And again, those x and y variables are needing that subscript of 1 because you're getting it from this table. All right, so let's go to begin. We have 83, 71. Let me show you that one more time. You're going to do the plus, you're going to go to the table, and then you're just going to start putting in your points. So we have 83, we have 71, we have 64. Again, these are the same numbers that I used in the calculator demonstration in the other video link. And then we have 171, 178, and 176. Okay, so we don't need this last row. Now, I have to test it, and I have to see the correlation coefficient on all of these, okay? So let's first create an equation that we think that it's going to be a linear function, okay? So I'm going to go first linear, then quadratic, and then exponential. So we are thinking it could possibly be linear. So we're just going to type in y1, and it'll jump down as a subscript. And then you're going to press shift and this key to the left of the number 1 on your keyboard. Okay, it looks like a squiggly tilde sign is what it is. Okay, so instead of that apostrophe, you're going to click shift and it creates that tilde. Ooh, I didn't realize that 2 tildes is an approximation. But we just need 1 for the regression. Okay, and then again, we're going to do this form of mx plus b. Okay, so let's go to m and then x1, and you see that it automatically jumps down there as a subscript, and then you're just going to do plus b. Okay, so this is my equation, linear regression, that it could be. And you're probably saying, well, where's the graph? Where are the points? Well, notice that the y values are actually pretty big, so you might have to like zoom out from here or you can kind of pinch it with your fingers like you would do on your phone, and then kind of zoom in into the important stuff. These are the points that I plotted right here. Okay, so the 5 points here are reflected here, and if you were to click on them, you could see there's 69, 176, and so on and so forth. Okay, so maybe it's linear. Okay, this one is a little bit hard to see because it doesn't really have a pattern. So if you're going to eyeball it, it's a little bit difficult on some of these. That's why we were going to depend on this correlation coefficient. Let's think that it's quadratic. Okay, so this form here, I'm going to go ahead and type it in, y1, notice the subscript, shift that key next to your number 1 on your keyboard, okay, and then it will be, let's go back, ax squared plus bx plus c. So ax1 squared, okay, then kick down to the right, plus bx sub 1, okay, and then plus c. Remember, the x and the y need the subscript of 1. All the other variables, just leave them as they normally would be, okay? So there's my quadratic regression. Kind of goes through it like the center-ish of all those blue points. And we also see r squared value. In other videos, you'll know that if I take the square root of that, it'll give me the correlation coefficient of r, which is the strength. So you see right here, it doesn't necessarily always do that for us. It'd be nice if it did every single time, but the way the Desmos and calculators are programmed, sometimes you do have to take the square root of the r squared value that you're given. Okay, let's do the last one. The last one is our exponential model. So we're going to say y1, again, shift tilde, and it's ab raised to the power of x, okay? And we need that subscript of 1, because again, we are grabbing from this table up here with our input and output. And there's an exponential function, okay? So if I zoomed out, the exponential function is the black one, and it shows you how it grows fairly rapidly as you keep going to the right, where that first one in black was the linear function, and then the other one in purple is the quadratic. Okay, so the bolded one here is the exponential, this is the linear, and this right here is the quadratic. Now we just have to do one more thing. We are in exponential and logarithmic functions unit. So when we use Desmos, if we use Desmos, which again, I hope your first go-to is that Inspire calculator, you're going to have to enable log mode. Okay, so if you did this with a logarithmic function or an exponential like we're doing here, you have to click, this is very important, you have to click and check this log mode in order to get the correct information. Because you see 138.966 is different than if I have it unchecked. So this is very important for you to get the correct answer. It has to be checked. All right, so now let's look at the strength of these correlation coefficients. And if you remember, the strength of a correlation coefficient is talking about its R value. So if I were to draw you a quick little picture, all right, let me go ahead and go to my other screen. And I'm talking about R, otherwise the correlation coefficient. The stronger it is, here's 1, here's -1, and here's 0. So the stronger it is to 1 or the stronger it is to -1, basically the closer it is, it's stronger as you get closer to 1 or as you get closer to -1, okay? But as you get closer and closer to 0, like things in between, anything around here in gray, it's going to be weaker. So you don't want to follow that model because its data is weaker. It's not as dependable or reliable or predictable that we can use that as a model. Okay, so we want to get closer to 1 or -1. So if I come over here and I look at these R values, I know that the linear function is 0.6936. Okay, so 0.6936 is the strength of the linear one. If I want to look at the quadratic, I'm going to find R, which unfortunately is not here. So I'm going to have to take the square root of 0.5125. So let's take the square root of 0.5125, and there we go. So that one's a little bit stronger, okay? So we have 0.6936, which you could say is probably about right here, 0.6936. This is the linear model, okay? And then you have 0.7158 or 0.7159, which is closer. We'll say 0.7 what were those numbers again? 159. And this is the quadratic, so it's stronger. So far, it looks like it's going to be quadratic. And then last but not least, let's go to the logarithmic one. Well, it gave it to us, okay? It gave us that r is equal to 0.6847. And notice here, if you don't have it checked, it doesn't give it to you, okay? So conveniently for us, we know we need to have it checked, and it also gives it to us, 0.6847. So if I come back over here, 0.6847 is about here, 0.6847, and this is the exponential model. So this is even weaker than the linear one, because again, we want to get as close to 1 or as close to -1 for it to be stronger and more reliable. Okay, so it looks like this one is going to be quadratic. So the equation that you would write out would come from the a value, b value, and c value that you have here. So let me go ahead and transition over back here in just a bit. I'm going to write out these a values, the a, b, and c values. So we have a is 0.026, and I'm doing this to 3 decimal places. B is -3.330, and then C value is 277.983. Again, we're wanting to go to 3 decimal places. That's 3 numbers after the decimal point as a minimum default, unless the question otherwise specifies something other than that. So we're going to go over here. You see that I wrote A, B, and C down here below quadratic. So I'm just going to replace those values. This A value is going to go over here where the equation would have gone. And this B value, whoops, let me get a different color highlighter. This B value is going to go right here. And then last but not least, you could say this C value is going to go right here. And that's when it matches up the other example that we did in the Inspire, where we wrote out y is equal to 0.026x squared plus a negative, so that's minus 3.330x, because again, we're just replacing those constants, and then we have plus 277.983. Let me move that over just a little bit, and then we have 0.983. Again, remember, this C value that we substituted in became in the equation the constant there at the end. The B value, which transferred over to the standard form, is going to become this negative 3.330. And then last but not least, what you did was you transfer that A so that you could write it here to 3 decimal places. Okay, so that's how you do it, guys. Just want to make sure that you remember, please click on this log mode to enable it. That way it gives you the correct A, B values and so on and so forth. All right, you guys have a